Hi everyone, in today's video I'm going to go into quite a bit of detail into the cyanotyping process, and I'm going to go into some of the deeper mechanics and science behind it, but before I do that I want to show truly how simple this method is. First you take equal parts reagents A and B and mix them in a cup. Next you put some on a brush, usually a sponge brush, and then you paint it on some cotton-based paper. Next, you can place something on top of the paper and expose it to UV light, which will allow it to develop. And now you have a completed cyanotype. One thing that really illustrates how unique this method is the darkroom itself. You can see in the light trap there's a light on, and if we look inside the darkroom, there's light dumping straight into it. You also likely notice that the light in here is yellow and not red. This is because this photo development method is only sensitive to UV light, unlike a lot of traditional methods. This is also why light leakage is such a small concern. Most LED and fluorescent bulbs have very small amounts of UV light, and therefore interfere with the method a very small amount. This is in stark contrast to a more traditional darkroom. As you can see, there's clearly no light in the light trap. And to go in here, you have to make sure that there is absolutely no light on you. In fact, to record this, I had to actually take out my earbud because it had a very tiny blue light on it, which could potentially react with any photosensitive materials in here. Although that begs the question, why is red light safe to have in here? And that's because red light is actually the longest wavelength of light that humans are able to see, meaning that it is low energy and minimally reactive with photosensitive material. Now at the beginning of the video I showed just mixing two liquids together, but this actually isn't the preferred way of doing this, because this solution tends to clump up when left for a while, so it's usually better to start from a powder. So that's what I'm doing here, working with this old-timey scale. I thought it was actually really cool to use one of these though, because it made sense why in a lot of lab sciences they refer to the scales as balances. Because that's exactly what you do with this type of scale. You load it with the weight and then you balance it. Right here what I'm making is solution A, which is an aqueous solution of potassium ferrocyanide. And then I store it in a light-proof reagent bottle. And then I started measuring out some ferric ammonium citrate for reagent B. And now with both reagents prepared, I can make the main solution. And right here I'm using some watercolor paper because it is cotton-based and fibrous, which makes it actually absorb the paint that I'm putting on top right here, rather than just sit on top. And just off screen I'm hanging it up to dry. Now before we continue my project, I wanted to show what some other people have done with cyanotyping, because it's a really expressive and creative medium, and I feel like I used it more so as just a printing method. So I'll leave links to all these creators in the description and I'll have their ads on screen. I thought this was such a unique project because not only is it showing how you can print physical objects, but this person's doing it onto some genes and it gets a really cool result. Going back to what I said earlier, I'm more so using cyanotyping as a printing method. I incorporate what I would call unique creativity later on in this project, which you'll see. But right now what I'm doing in Lightroom is adjusting my tonal range to get what I want, and then importing it into Adobe Photoshop and using a template to get it ready to print on a specific type of paper for negatives. And here's the paper I was referring to earlier. It has a gelatin coating on the front of it, which allows a matte ink to stick to it. I always love sticking a tiny normal size sheet of paper into this massive printer. And here's what the photo negative looks like. And now we return back to the dark room, although you'll notice that this part of the dark room is not especially dark. But this is the step where we expose it to UV light to create the dark blue color. A lot of times this is done just by leaving it in the sun, but in this case I'm using a special machine that has UV lights built into the top and a pane of glass that vacuum seals over the top of the paper and negative. This is also an exciting step because this is when the chemistry officially begins. As of right now, no reaction has actually taken place, and right now on screen I have the molecules that we've put on the paper. Now these are incredibly hard to represent, and that's why it looks like we have so many molecules. There's actually only 2 molecules on here right now, and that's because these are very large ionic compounds, and due to them being ionically bonded, that means that they are not actually truly chemically bonded. And it causes us to have to represent it more like this. Now without going into too much detail, I want to take a look at this molecule on the left. So the first thing, the ammonium, is considered a spectator ion, which means it just serves to balance out the charge of the molecule. It doesn't actually contribute to the reaction. The next part of the molecule to consider is the citrate. In this case, it is serving as a ligand, and without going into too much detail, that means that it bonds to the iron in specific spots. In this specific case, the citrate binds to the iron at 3 different binding sites, although it forms a very weak bond. Now here's where it gets exciting, because when the Fe3+ ion gets blasted with UV light, the electrons around it get so excited that it changes to the Fe2+ oxidization state. And now that it's in a new state, it doesn't want to stay bonded to its ligand, and it'll instead go over towards the other molecule and replace the potassium to balance the charge. And finally you end up with a massive molecule that looks kind of something like this. Again, this is an ionic compound, so it's very hard to represent. But this molecule is called ferric ferrocyanide, or more commonly, Prussian blue. Now that that exciting reaction happened inside of this device, we can open it up and take a look. And at this point, it doesn't have that rich blue that I showed at the beginning of the video. This is for 2 reasons. 1, the unreacted chemicals have not been washed away, and 2, the iron hasn't had a full chance to oxidize yet. Right here I'm making a solution to wash away any unreacted chemicals and to oxidize the rest of the iron. It contains vinegar and water to wash away the unreacted chemicals and hydrogen peroxide to speed up oxidization of iron. And here I am using the solution. Now, you can clearly tell that the video is sped up quite a bit, but this reaction is really quick and it's almost magical seeing the photo come to life. And then finally I used this tub with holes drilled in the back of it to run water over the top of the cyanotype to wash away all the vinegar and hydrogen peroxide. And then I hang it up to dry. Now that it's dried, the cyanotype is officially complete. However, that doesn't necessarily mean that it's time to stop. Going back to our Prussian blue pigment, we can actually disrupt the structure and replace it with something else. To do this, we need some hydroxide ions, which we can get easily by mixing water with a base, which will steal the hydrogen off the end of the water molecule and form hydroxide. Now the hydroxide will attack the iron cyanide bonds and break them apart, opening back up the binding site to other molecules. So here I'm preparing the bleaching solution, just some ammonia and some water. Now I'm putting in the cyanotype, and you'll see that it actually turns a slight purple color before it starts to fade. And now I'm just preparing a quick cleaning solution with vinegar and water to help wash away all the ammonia. And here I am repeating the process with a different cyanotype. This one's a little bit darker, so I think it shows the process a little bit better. Now going back to the destroyed pigment, we have these binding sites I was talking about, and one thing that binds very well to this is tannins, or tannic acid, which is found in coffee, tea, and wine, or can be bought as a reagent. So here I am immersing a cyanotype in wine. Now I did try to do one without bleaching at first, and it didn't work, and for some reason I didn't record the actual take, so this is the one you get for this. And here's the final result of the cyanotype toned with wine. I did have to add some tannic acid to make the darks a little bit darker, but I think it turned out really well. And here's the cyanotype that I toned with coffee. I think it also turned out really well. I did not have to add any tannins to this one. And this is my untoned cyanotype. And here they are all together as one artwork. Thank you so much for watching this video. I really enjoyed the process and I really enjoyed explaining it to you guys, and I hope you learned something along the way.